Hi, and welcome to 9.2 Impulse-Momentum Theorem. The theorem is just like a big long equation, a lot of different parts to this equation. So it's saying that the impulse, which is represented by a J, is equal to the change in momentum. By definition, anytime you have a change in momentum, it's because an impulse was acted on it. What is an impulse? It's just a force that's being exerted over a certain amount of time. It could be a short time of impact and a high force, or maybe you stretch that force over a longer time of impact, kind of like an airbag in a car slowing you down to a stop. You still have the same change in momentum. Overall change in momentum is the same. It's just that if you increase the time of impact, you decrease the force to have the same impulse or change in momentum. That's what the formula is all about, and technically this is the net force. I'm going to derive the formula just for fun. Feel free to skip this if you already know where the formula comes from. But I like to derive the formula because at first glance it looks like just a bunch of letters. Where is this coming from? The great thing about physics is that everything is set in the real world and it actually means something. So I feel like if you understand that, it makes the problems and it makes using the equation a little bit easier. Okay, so the impulse-momentum theorem, it comes from the idea that anytime you want to change something's momentum, you're imparting what they call an impulse on it. So we're going to use this formula. We're going to go back and we're going to use a kinematic equation, the definition for acceleration, your change in velocity over time. How fast are you changing your velocity in a certain amount of time? That's your acceleration. And we also have Newton's second law. The acceleration is equal to the net force divided by the mass. So we're going to use these three equations in order to come up with the theorem. So we'll start with this. J is equal to the change in your momentum. Also, we know the momentum is equal to mv, so it's really four equations. So this is equal to pf minus pi, your change in the momentum. Now we know that momentum is equal to the mass times the velocity, so we have to plug that in for each one. You have an initial velocity and then maybe you slow down or speed up. You have a final velocity, therefore your momentum changes. So the mass times the final velocity minus the mass times the initial velocity. Okay, now you see mass is in both terms, so we could take that out. And we have J is equal to the mass times Vf minus Vi. And we could rewrite that as just the mass times the change in the velocity. So now we have the impulse is equal to the change in momentum, which is also equal to the mass times the change in the velocity. Now let's figure out, okay, what is delta V equal to? Well, the acceleration is equal to the change in velocity over time. And if you cross multiply, you'll see that the change in the velocity is equal to the acceleration times the time. So anywhere we see a change in velocity, we're going to plug in acceleration times time. So let's rewrite our equation. So the impulse is equal to the mass, not delta V. Let's write in A times T now. We plug this in for delta V. Now we have the impulse is equal to mat, but nobody likes mat. It's not that nice. So we want to rearrange it. Now let's use this guy. All right, how can we get an MA out of that formula? Well, you might remember Newton's second law. It states that the net force is also equal to the mass times the acceleration. We did the same thing. We cross multiplied. So the net force is equal to the mass times the acceleration. And now anywhere we see an MA, we could plug in a net force. So we could rewrite this as the impulse is equal to the net force times the time. And now we have a third equation, and we're done. This is great, but it's all piecemeal. It's all over the place. So let's just write it out in one nice big line. We could say that the impulse is equal to the change in momentum, which is equal to the mass times the change in the velocity, which is equal to the force, the net force, times the time. And this my physics friends, is the Impulse-Momentum Theorem, a big, long equation that we could use to solve a lot of different problems. Maybe the problem gives you the mass and the final velocity and the initial velocity. You definitely want to pull this guy out. And maybe they're looking for the impulse, so you pull this guy out. So you just pick and choose which part of the theorem you want to use to make a useful equation for whichever situation you're talking about. Now, I will note one thing. On the physics reference table, the New York State physics reference table, it doesn't include this because this is just saying the same idea, that it's the change in the momentum. Technically, you could also have a change in mass times your velocity. Maybe you're moving at a constant velocity, but you're changing your mass. Or maybe you're changing your mass and you're changing your velocity. All three of these things are saying the same thing. It's saying you're changing your momentum. So on the reference table, it doesn't include this version of changing the momentum. But I like to include it because 9 times out of the 10 in these types of problems, you're changing your momentum because your velocity is changing, not necessarily your mass. Anyway, that is the Impulse-Momentum Theorem. Let's do some problems. Okay, very good. So there's the Impulse-Momentum Theorem. Let's add in that other piece, and let's move it to the top of the screen. Okay, looks like there's a lot of different parts to this one. It says, answer all questions completely, show all work, and substitute with units. Then it says, a car with a mass, so the mass is 1,000 kilograms, is at rest at a stoplight. So that means it's not moving. Its velocity is 0 meters per second. When a light turns green, it's pushed by a net force of 2,000 newtons for 10 seconds. So they tell you the net force is 2,000 newtons, and the time is 10 seconds. So now you're accelerating because you have a net force. The forces aren't balanced. You're being pushed in one direction. You're picking up speed. So this is actually the initial velocity. You start at 0 and then you speed up. And number 1 says, what is the value of the acceleration that the car experiences? So A is equal to question mark. Now, this is where the guess method comes into play because they're looking for the acceleration. These are all the different things that you know. Now you have to find an equation. Which equation should I use to find the acceleration? You might think that since this is the Impulse-Momentum Theorem, we'd want to do something like this in here. And technically, you could rearrange it in a certain way. You could do the opposite of the derivation that we just showed. But since we know what the mass is, and we know what the net force is, and they're looking for the acceleration, we should just use Newton's second law to figure out what the acceleration is. So Newton's second law states that the acceleration is equal to the net force divided by the mass. The net force is 2,000 newtons divided by 1,000 kilograms. So the acceleration is equal to 2 meters per second squared. There you go. Now that's another piece of given information that we could use. It says, what is the value of the change in velocity that the car experiences? So it's not saying what is the final velocity. No, it's saying what is the change in velocity. So they're looking for delta V. So if we're looking for the change in the velocity, we have a choice. I mean, we could do the acceleration is equal to delta V over t. Actually, and that's probably the best way to do it. So the acceleration is equal to 2 meters per second squared. That's equal to the change in the velocity over the time, which is 10 seconds. So you change your velocity by a value of 20 meters per second. So that's the answer. Now, as a side note, technically, that is the final velocity as well, because your change in your velocity is equal to Vf minus Vi. You changed your velocity by 20 meters per second. If you're looking for your final velocity, you're subtracting your initial velocity, which is 0. So the final velocity is actually the same as your change in the velocity due to the fact that you started at rest. All right, so that's the idea, just as an aside. Now that we know the change in the velocity, and we actually know the force and the time, it should be pretty easy to find the impulse. So they're looking for J. What is the impulse acting on the car? Now, like I said when we derived it, we have 1, 2, 3, 4 pieces in this big long theorem, this big long equation. We only need 2 of the pieces to solve. All right, we only want 2 pieces. So you have to pick and choose which pieces do you want to use. Well, they're asking for the impulse, so we definitely want to make sure we choose this guy. So J is equal to. Now, we have to be careful. Do we want to look at delta P? Do we know the final and the initial momentum? I don't see it anywhere over here, no final or initial momentum. So let's not use that one. That'll make our life a little bit harder. How about this guy, M delta V? Do we know the mass? Yup. Do we know the velocity? Yup, we just found it, so that's good. So we could definitely say J is equal to M delta V. There is another way we could do it. If we look for the force times the time, they tell you that it's a net force for 10 seconds. So you could actually use another equation to find the impulse. Both are valid. The net force times the time. So let's see what we get. Let's do them both, just in case some people did one way, some people did the other. So the impulse is equal to the mass, 1,000, times the change in the velocity, which is 20. So you get 20,000 Newton seconds, kilogram meters per second. Or you could solve it this way. The net force is 2,000 newtons, and the time is 10 seconds. So you get an impulse of, again, 20,000 Newton seconds. And now, since we have this piece to the puzzle here, the units of Newton seconds should make a little bit more sense. The units for force are newtons, and the units for time is seconds. So therefore, the units for impulse can be Newton seconds. But they could also be kilogram meters per second, because it's just the change in the momentum. So that's equal to the impulse. So you could have either one. If you write both down, that's fine. Even if you wanted to say that something has a momentum of 5 Newton seconds, you'd technically be correct. And I have to show you why. Okay, so how can a Newton second be equivalent to a kilogram meter per second? They look very different to me, right? So let's figure out, what is this Newton anyway? All right, the force is equal to mass times acceleration, right? So we have mass is in kilograms, acceleration is meters per second squared, and we made force, we called it a Newton, but we could just call it a kilogram times a meter per second squared, because it's a kilogram times a meter per second squared here. All right, so that's actually what a Newton is equal to, a kilogram meter per second squared. Okay, knowing that, let's plug that in over here. So let's take that idea, erase that, and let's take it over here. So we have a Newton is equal to a kilogram times a meter per second squared times a second is equal to a kilogram meter per second. Is that what we're saying? Well, if you have a second divided by a second squared, you cancel out one of the squared seconds. So now we have a kilogram times a meter, and it's all over just 1 second. This has gone away now, and there's only one of those down there. And now we have a kilogram meters per second, which is equal to a kilogram meter per second. So yes, it is true that a Newton second is equal to a kilogram meter per second. So you could use those for impulse, or you could use those for momentum interchangeably. You could make maybe momentum is a Newton second, and impulse is a kilogram meter per second. Both are fine, but typically people think of impulse in terms of Newton seconds, because you're exerting a force over a certain amount of time in order to change the momentum. In order to give an impulse, you need to exert a force over a time, or over a period of time, so a force times time. And then people think of momentum in terms of kilogram meters per second, because you want to think about the mass of the object and how fast it's going when you're calculating the momentum. All right, back to the question. Okay, that was a bit of a tangent, but an informative one. Now, 4 says, what is the value of the change in momentum that the car experiences? So they're looking for the change in the momentum. And the impulse-momentum theorem, let's look at it. They're looking for this guy. So let's use that. Now we have a choice. We could use the impulse, which we just found, or we could use the mass times the change in the velocity, which we know, or we can also use the force times the time, which they tell you, in the problem. Okay, so you have your choice. Now for me, I would choose the easiest one. By definition, the change in the momentum is equal to the impulse. So let's use these two guys. And there's actually no formulas necessary for number 4. The change in the momentum is equal to the impulse that we found in the previous part, 20,000 Newton seconds. In other words, 20,000 kilogram meters per second for your change in the momentum. Okay, number 5. What is the final velocity of the car at the end of the 10 seconds? Oh, we just discussed that up above with the with our aside that we made, right? So we had said that the change in the velocity is equal to, we calculated it, 20 meters per second. We know the initial velocity, it starts at rest, so it's 0 meters per second, and they're looking for VF. So by definition, the change in the velocity is equal to VF minus VI. So you just plug in, this is 20. VF is what we're looking for. VI is actually 0. So the final velocity is equal to 20 meters per second. It's equal to the change in the velocity in this case because you're at rest. Okay. Then it says the car continues at this speed for a while, at this speed here. All right, so it's moving at 20 meters per second. What is the value of the change in momentum the car experiences as it continues at this velocity? Hopefully, conceptually, you're able to find the answer. If you're moving at a constant speed, what is your change in momentum? Did you say 0 kilogram meters per second? You'd be right. But why, right? So what are we saying? Can we show it mathematically? All right, let's see. Your change in your momentum is equal to your mass times your change in the velocity, right? So let's see. Your change in the momentum is equal to the mass is 1,000 kilograms, and your change in the velocity is VF minus VI. So you can, instead of VF, you write 20 because you stay at the same speed the whole time, and your initial velocity is also 20. So 20 minus 20 is 0, so your change in your momentum is equal to 1,000 times 0. You didn't change your velocity, so 1,000 times 0, your change in momentum is equal to 0 kilogram meters per second. But technically, you didn't really have to do any calculations for that because you should just know if you're not changing your velocity, not changing your mass, you're not changing your momentum. Number 7, what is the value of the impulse on the car as it continues at this velocity? Well, again, we could revert back to the impulse-momentum theorem. We know the change in the momentum is 0, and they're asking for the impulse. So we could set up that formula again if we wanted to. The impulse is equal to the change in the momentum. The impulse is equal to, the change in the momentum is 0. So it's 0 Newton seconds, or 0 kilogram meters per second, either way. All right, so nothing's really happening. It's just moving at a constant velocity. Okay, the brakes are applied to the car, causing it to come to a rest in 4 seconds. So now it says, what is the value of the change in momentum that the car experiences? It's kind of like almost a new problem now. All right, so you have to visualize the car is moving. All right, this is your car. Very nice car. And it's going, the velocity is now initially 20 meters per second. And then it comes to a stop. It looks more like a truck. And then the final velocity is 0 meters per second, right? So it says, what is the change in the momentum? Actually, we should already know from the previous problem what it's going to be, but we could calculate it again, right? So let's set it up. The mass is still 1,000 kilograms. Your initial velocity is 20 meters per second. Your final velocity is equal to 0 meters per second. Now we can use actually the impulse-momentum theorem to find an equation. All right, given this, we're looking for delta P. So we better use, let me bring this down there. Okay, we better use this part of the equation because they're looking for the change in the momentum. And also, we know the mass and the change in the velocity, so we can use this part of the equation. So this is equal to m delta v. So this is equal to, the change in the momentum is equal to the mass times vf minus vi. So the final velocity is 0 minus vi is 20. So the change in the momentum is actually equal to negative 20,000 kilogram meters per second. And the negative matters. It's wrong if you don't put the negative, because your car is moving and it's moving to the right. But now something is acting on it, slowing it down. Its momentum is to the right, but now the momentum vector, the change in the momentum, is slowing it down to a stop over here. Now your velocity is equal to 0 meters per second, so your momentum is equal to 0 meters per second. There must have been some kind of force acting on it to slow it down this way, to cause you to accelerate in this direction, meaning that you have an impulse acting against your velocity, slowing you down to a stop. So your momentum is changing in the negative direction. All right. If it was changing in the positive direction, that would mean that you're speeding up. You're getting more momentum in the positive direction, but you're not. You're slowing down. So the vectors oppose each other, slowing it down. Okay, so that's the idea. Now it says, what is the value of the impulse on the car? And again, so we're looking for J, the impulse. So we better use that part of the equation. And we already know the change in the momentum, so we can use that part of the equation. So even though the impulse-momentum theorem looks really complicated because it's this big, long string, sometimes you'll luck out and they'll ask a question like that. So the impulse is equal to just to negative 20,000. And then I call it Newton seconds because now we're talking about an impulse. So that's what slowed you down. This impulse of negative 20,000 Newton seconds is slowing you down, opposing your motion, slowing you down to 0 meters per second. 0 kilogram meters per second for the momentum. Number 10 says, what is the value of the force that causes the car to stop? So now they're looking for the force, the net force. And visually, we could probably figure out the net force is also going to be negative. It's the thing that's slowing you down. And it's in this part of the equation. So let's use that. The net force times the time. We should try to use that. They tell you the time is 4 seconds, so that's good. Could have wrote that down before. All right. And the impulse and the change in the momentum. Now we know both of these pieces, so it depends on what you want to write in as your second part of the equation. All right, but you could write whatever you want. So this is the net force times 4 seconds is equal to negative 20,000 Newton seconds. All right, so the net force is equal to 5,000 newtons in the negative direction. All right, pointing to the left, slowing you down, which is more than the initial force that started you going. You were accelerating at a slower rate because of this, the decreased force, right? It was less force, 20,000 newtons initially, and then you go at a constant velocity, and now you slam on the brakes, and a larger force causes you to stop in a smaller amount of time. As opposed to 10 seconds, now it's only 4 seconds. And it says, what is the acceleration of the car as it stops? There's no acceleration up here, so that's not going to help us as much as Newton's second law, which is the net force divided by the mass. I interchange between writing that force like this and writing net force like that. Doesn't really matter, whatever you feel like doing. So this is equal to negative 5,000 newtons divided by, it was a 1,000 kilogram car. So your acceleration is equal to negative 5 meters per second squared. So your acceleration vector is also pointing to the left, slowing you down. Anytime your velocity is opposite your acceleration, you're going to slow down. All right, very good. Number 12. All right, this is some good advice here. Make sure you read that. It's basically just saying don't just look at the math and the formulas and not try to conceptualize what's happening. I try to explain it like that. I try to draw pictures. It's just basically saying visualize what's happening. Don't just take this theorem at face value and start plugging things in, because you might get tripped up with some tricky questions. So let's try number 12. It says a force of 800 newtons causes a 80 kilogram fullback to change his velocity by 10 meters per second. Determine the impulse experienced by the fullback. So the force is 800 newtons. The mass is 80 kilograms. And the velocity, all right, its change in velocity is 10 meters per second. So it's looking for the impulse. And we could use the theorem here. Okay, they're looking for the impulse, so we better use that part of the equation. So J is equal to, now look what we have. We have the force, so maybe we should use this guy. Well, we don't have the time of impact, so we can't really use that. But we do know m and the change in the velocity, so let's use this piece right here. So the impulse is equal to m delta v. And then you don't have to worry about this anymore. So once we use the big long theorem and we break it into a useful equation that's only two pieces, we could just work with that. So the impulse is equal to the mass times the change in the velocity. So the impulse is equal to 800 Newton seconds acting on the football player. Okay, so now 13 says a 0.8 kilogram soccer ball. So the mass is equal to 0.8 kilograms. Experiences an impulse of 25 Newton seconds. What is the momentum change of the soccer ball? So this is the change in the momentum. What's the change in the momentum? Okay, so let's use what we know again. So we're looking for delta P. So we might as well use that part of the equation. And then what else do we know? We know the mass, but we don't know the change in the velocity. And luckily they tell you the impulse, which makes our lives a lot easier, because by definition the impulse is equal to your change in the momentum. So your change in the momentum is equal to 25 Newton seconds, or 25 kilogram meters per second. You change the momentum of the soccer ball by 25 kilogram meters per second. Maybe you slowed it down, maybe you sped it up, but it changed by 25. 14 says the mass, a 1,200 kilogram car, is brought from, so your initial velocity is 25 meters per second. Your final velocity is 10 meters per second. Over a time period, so t is equal to 5 seconds. It says determine the force experienced by the car. Okay, so we have the mass and two velocities, so we could use this guy. And they're looking for the force, and they give us the time, so luckily we could use that guy as well. We actually don't need either one of those, so we don't need impulse or momentum in order to use the Impulse-Momentum Theorem. We could just use these two guys. So m delta v is equal to the force times the time. You could get away with just using those, because if you look at our given information, we have everything we need. So the mass times the final, always do VF minus VI. So VF comes first, so 10 minus 25. That's important because it's going to show you the direction that the force is acting. Is it positive or negative? So the net force times 5. So now you have 1,200 times negative 15. So you get negative 18,000 and that's in terms of kilogram meters per second or Newton seconds, is equal to the force times 5. So to find the force, you would take the momentum and divide it by 5. And now you get 3,600 newtons pointing to the left, negative. So if you think of your car, I'm going to try to draw a nice car. Okay, so there's the car, and you have an initial velocity of 25 meters per second. So it's moving pretty fast. But now it's coming to a stop. Oh no, it's just slowing down to 10 meters per second. So the final velocity is 10 meters per second. And in order to slow down, what direction did you have to exert your force? Your force must have gone in the opposite direction. They're slowing you down to only 10. Very nice, very nice. Okay, number 15. A 90 kilogram, so the mass is 90 kilogram, tight end moving, so the velocity is 9 meters per second, encounters a 400 Newton second impulse. Determine the velocity change. So delta V. What is the change in the velocity of the tight end? Okay, so we're looking for delta V. So we have to figure out which part of the Impulse-Momentum Theorem has delta V. And it looks like this piece does. And luckily we have the mass, so we're in business. We could definitely use m delta V in our equation. And they also tell us the impulse. So we can just use the J part of the equation there. And that's how I would solve this one. You don't have to mess around with like, well, can I find the force given that? It doesn't tell you the time, so that you can't find the acceleration. So this is the best way to do it. This is 90 times delta V is equal to 400. So your change in your velocity due to this impulse is 4.4444 meters per second. Okay, number 16 says a 0.1 kilogram hockey puck, so the mass is 0.1 kilograms. It decreases its speed from 40 meters per second, so VI is 40 meters per second, to a rest, 0 meters per second. So the time is 0.25 seconds. It says determine the force that the puck experiences. All right, it should say determine the net force. All right, because technically we're looking for the net force. How do I know that? Because that's what the theorem says. So if we're looking for the net force, let's try to use this guy. Luckily, we have the time, so we're off to a good start. The net force times the time. What else should we use? What else do we have? That's the real question. We have mass and 2 velocities, so we should probably use the mass with the change in the velocity. So this is m delta V. So the net force times the time is equal to the mass times the change in the velocity. Now technically this is VF minus VI again, right? So this is the final velocity is 0 minus 40. So you're going to get a negative number. So the net force times 0.25 is equal to 0.1 times negative 40, which is equal to negative 4. So the net force is equal to negative 4 divided by 0.25. Negative 4 divided by a quarter should give you negative 16 newtons. So again, the force is negative. It's kind of like the car problem up above, because you have the hockey puck coming in at a velocity of 40 meters per second, and it slows down to a stop. So it's fast lines. And now the velocity, the final velocity is 0 meters per second. Well, how did it slow down? There must have been a force acting in this direction, in the negative direction left, in order to slow it down, give it that acceleration in the negative direction. So both the net force, the acceleration, and the impulse, you could say, are pointing to the left. All right, there's just 3 different ways to think about why this thing is slowing down. Okay, now it says a real brain twister. Oh man, get ready for your brain to be twisted. Let's see. Let's move down the screen a bit. So now it's talking about the hockey puck again. So it says the mass of the hockey puck is 0.1 kilograms. It's at rest, so VI is equal to 0 meters per second. And it encounters a force of 20 newtons for 0.2 seconds. And it sets it into motion. Over the next 2 seconds, it encounters a 0.4 newtons. Also, this is like F1 time 1. F2 is 0.4 newtons. And it says it acts on it over the next 2 seconds of resistance force. So maybe there's like very slight friction between the ice and the rubber puck. Finally, it encounters a final force, so F3 of 24 newtons for 0.5 seconds. So the time is 0.05 seconds in the direction of its motion. Ooh, that's interesting. They're kind of giving you a clue here. Maybe we missed something in terms of the direction of these forces. It says, what is the final velocity of the hockey puck? So you have your puck. It's initially at rest. Then you push on it, so there's a force being exerted this way, giving it a new velocity, all right? But we don't know what the velocity is. So V1, we don't really know. Then it says over the next 2 seconds, it encounters, this is resistance force. So now there's a very little force of resistance opposing you, and it's slowing you down. All right, so we don't know what V2 is, but we know it's going to be less than V1. And now it says finally encounters a final force of 24 newtons for 0.05 seconds in the direction of its motion. So I'm going to assume that it's still going to the right, right? All this time it's going to the right. And it might not be. That's a dangerous assumption. I'm just going to double check. So this is now another force. So this is F1, this is F2, this is F3 in the direction of its motion. Let's assume that its motion is still to the right. So we'll go like this. It's still, we don't know what it is, but going like this. And they want to know what the final velocity of the puck is. So we're looking for this guy. All right. Seems complicated, but let's just do it. Let's try to do it in like just a couple steps. Well, first of all, we want to make sure that the second force is going to be negative. So let's put a negative sign there. And now you're constantly changing your velocity. You're changing your velocity here, changing it here, changing it here. And in the Impulse-Momentum Theorem, we could calculate what each one of those is by doing like the force times the time. So if it's F1 and T1 is equal to the mass times your change in your velocity. So the force times the time in this case would be 20 times 0.2, and then this is 0.1 times delta V. So you get 20 times 0.2. That's going to be 4, and that's equal to 0.1 times your change in your velocity. So now you divide, and your change in the velocity is actually equal to 40 meters per second. So now we know V1 is equal to 40 meters per second. And we could keep doing the same thing. We could do for F2 and T2. So this is negative 0.4 times 2. So you get 0.8 is equal to the mass times the change in the velocity. Oh, sorry, this is negative, so now you have negative 8. You change your velocity by negative 8 meters per second. So if you want, I mean, conceptually, hopefully you're able to say, okay, it was 40. I'm changing it by negative 8. So now this should be 32. If you needed an equation, you could say, okay, the change in the velocity is equal to VF minus VI. We kind of skipped the stuff in the previous problem when we did this jump. But we started at 0 and changed our velocity by 40, so our final velocity was 40 there. Now you plug in your change in the velocity. We're looking for what our new velocity is. The initial velocity was 40 in the positive direction. So yeah, VF is equal to 32 meters per second. And then you could do it for the final step. You just do it one more time. Now it's F3, T3 for the third force. This is positive 24 newtons. Now we're sure of it because it's definitely still going to the right. We were at 40 and I wasn't sure. Remember it said it encounters 0.4. Okay, it finally encounters a force of 24 newtons in the direction of its motion. If this impulse was enough, if that force was enough to slow down and eventually turn around the puck, then this force would now be negative because it says in the direction of its motion. So it was a little vague there. We kind of like assumed, but looking at the force and the time, you could kind of predict what direction that was going to be, but we were right. This is a positive force. It is still moving to the right. So this is times 0.05, and you get 1.2, and then 1.2 divided by the mass is 12 meters per second. So you changed your velocity by 12 meters per second. It was 32 meters per second. So now you add it and you get 44 meters per second in the positive direction. So that is the final answer because it's asking what is your final velocity. And there you go. That was a lot of work. But if you look below here, it says you may have been tricked, but those are not intended as trick questions. Also, these were not intended to be like super hard and multiple step problems where you had to do it 3 different times. The questions were intended to test your understanding of the concepts of momentum change, impulse, mass, force, time, and velocity change. How is your understanding level progressing? Do you have formula fixation? I wonder if we could just do this in one formula. Let's see if I could squeeze it in the bottom here. All right, so for each of these forces, each force is causing an impulse. What if we were able to just find what is the total impulse? So that's equal to F1, T1 plus F2, T2 plus F3, T3. So the total impulse is equal to 20 times 0.2 plus negative 0.4. Again, that was another major key. You could do all this work, but get the wrong answer because you didn't make this negative. And the only way to know it was negative is because it says resistance. If it's a resistance force, that means it's opposing the motion. So if we made the velocity pointing to the right, this resistance force has to be pointing to the left. In other words, the force has to be negative. So that was another, you could do everything right, do all that work, and still get to the wrong answer because you didn't put it negative just because you didn't notice that it said resistance. So every word is important for the most part in these physics problems, unless they're doing something silly about like squirrels or something like that. But you know, even then, the key words are hidden in the word problem. And this is acting for 2 seconds, back to doing physics. Okay, so this is the force. The third force is 24 in the positive direction we determined times 0.05. So the total impulse is 4.4 Newton seconds. And that's good to know. So that's equal to the impulse. And now we could use the Impulse-Momentum Theorem and say, okay, we know what the impulse is, and we're looking for the final velocity, but we start at 0, so it'd be nice to know what the total change in velocity was, right? So this is the total. That'll give you your total change in velocity, your overall change in velocity. So if this is 4.4 and the mass is 0.1, then your change in velocity, is equal to 44. 44.4 divided by 0.1 is 44 meters per second. And we know we started at 0, so your final velocity is 44 meters per second. And that's all there is to it. All right, have a good day.